The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
So let's get started with the second lecture for today. So I guess one thing Multicore's did is it really shattered this nice view of writing single programs and hardware is going to take care of giving you performance. So hardware just kind of completely gave that up. So what we're doing in this class is really try and do it by yourself. Give all the responsibility back to the programmer. So and you'll realize as you go, it's a much harder job. I mean, this is not simple programming, and so you don't have MIT class students on every company to do this. So we need to have some kind of middle ground. And so some of the stuff we have been doing as research is trying to figure out, are there any middle ground? Can you actually take some of that load away from the user into things like languages and compilers? So we are going to talk about some of those effects. So right now we are kind of switching from directly giving you what's necessary to do the cell project into go a little bit breadth. So this lecture, and then we'll sit back a little bit into debugging and performance monitoring. That will be directly helpful. And then next week we'll have a bunch of guest lectures to kind of give you breadth in there. So you'll understand not just cell programming, but in parallel programming and parallel processing, what the world is like beyond that. So today we are going to have Bill talk about streaming.
Okay, very good. So my name is Bill Thies. I'm a graduate student working with Saman and Roderick and others here. And I'll talk about the StreamIt language. So why do we need a new programming language? Well, we think that languages haven't kept up with the architectures. So one way to look at this is that if you look back at previous languages, look at C with a von Neumann machine. Now, I grew up in rural Pennsylvania, not too far from Amish country, and so to me, these go together just like a horse and buggy. Okay, they're perfectly made for each other. They basically go at the same rate. Everything is fine. But the problem is, in comes the modern architecture. Okay, this is an F-16. You have a lot more that you can do than with a horse and buggy. So how do you program these new architectures? Well, architecture makers these days are basically faced with a really hard choice. On the one hand, you could get a really cool architecture and develop kind of an ad hoc programming technique where you're really just leaving it to the programmer to do something complicated to get performance. And unfortunately, I think that's the route that they took. I mean, fortunately for the industry, but unfortunately for you, I think that's the route they took with Cell, which means all of you are going to become basically fighter pilots. You have to learn how to fly the plane. You have to become an expert. You're going to become the best people at programming these architectures. And unfortunately, the only other option is to really bend over backwards to support the previous era of languages, like C and C++. And if you can see what's coming here, it's just hard to get off the runway. So you don't want this situation. Just out of consideration for whoever's in the buggy, hopefully you'll never take off. So looking from a more academic perspective, why do we need a new language right now? So if you look back over the past 30 years, I know you've seen this graph before. We were dealing with just one core in the machine for all this time. And now we have this plethora of multi-cores coming across the board. So how did we program these old machines? Well, we had languages like C and Fortran that really had a lot of nice properties across these architectures. So it was portable, high performance, composable. You could have really good software development, malleable, maintainable, all the nice things you'd like to see from a software engineering perspective. And really, if you wrote a program back in 1970, you could keep it in C and have it continue to leverage all the new properties of the machines over the past 30 years. It would just run fine out of the box. And looking forward, that's not going to be true. So for example, we could say that C was a common machine language. That's what we say for the past 30 years, was common across all the machines. But now looking forward, that's not going to be true anymore, because you have to program every core separately. So what's the common machine language for multi-cores? We really think you need something where you can write a program once today and have it scale for the next 30 years without having to modify the program. So what kind of language do you need to get that kind of performance? Well, let's look a little deeper into this notion of a common machine language. So why did it work so well for the past 30 years? Well, on uniprocessors, things like C and Fortran really encapsulated the common properties. So things like a single flow of control in the machine, a single memory image are both properties of the language. But they also hid certain properties from the programmer. So they hid the things that were different between one machine and another. So for example, the register file, the ISA, the functional units, and so on. These things could change from one architecture to another. And you didn't have to change your program because those aspects weren't in the programming language. So that's why these languages were succeeding. And what do we need to succeed in the multi-core era from a language perspective? Well, you need to encapsulate the common properties again. And this time, it's multiple flows of control that you have for all the different cores and multiple local memories. There's no more monolithic memory anymore that everyone can read and write to. Also, you need to hide some of the differences between the machines. So some cores have different capabilities. On Cell, there's a heterogeneous system between the SPEs and the PPE. Different communication models on different architectures, different synchronization models. So whatever common machine language we come up with, we'll have to keep these things hidden from the programmer. Now, a lot of different researchers are taking different tacks for how you want to invent the next common machine language. And the thrust that we're really excited about is this notion of streaming. So what is a stream program? Well, if you look at a lot of the high-performance systems today, including PowerPoint, which is running this awesome animation, you can basically see that they're based around some stream of data. So audio, video, like HGTV, video editing, graphic stuff. I think actually a lot of the projects in this class that I looked at would fit into the streaming mold. Things like the software radio, ray tracing. I probably don't remember them all, except when I looked at them, they all looked like they had a streaming component somewhere in there. So what's special about a stream program compared to just a normal program? Well, they have a lot of attractive properties. If you look at their structure, you can usually see that the computation pattern remains relatively constant across the lifetime of the program. So they have some well-defined units that are communicating with each other, and they continue that pattern of communication throughout. And this really exposes a lot of opportunities for the compiler to do some optimization that it couldn't do on just an arbitrary general-purpose program. And as you saw before, we have basically all the types of parallelism are really exposed in a stream program. There's the pipeline parallelism between different producers and consumers. There's the task parallelism, basically going from left to right. And also data parallelism, which means that a single one of these stages can sometimes be split to apply to multiple elements in the data stream. So when you're thinking about stream programming, there's a lot of different ways you can actually represent the program. So whenever you have a programming model, you have to answer these kinds of questions. For example, do the senders and the receivers block when they try to communicate? How much buffering is allowed? Is the computation deterministic? What kind of model do you have in there? Can you avoid deadlock? Questions like these. And we could spend a whole lecture answering these questions, putting them in different categories. But what I want to do, just to give you a feel, is touch on kind of 3 of the major models that you might see come up in different kinds of programming models. And I'll just touch on con-process networks, synchronous data flow, and communicating sequential processes, or CSP. So just one slide on these models. So let's compare them a little bit. First is the con-process networks. So this is kind of the simplest model. It's very intuitive. You just have different processes that are communicating over FIFOs. And the FIFO size is conceptually unbounded. So to a first approximation, it's kind of like a Unix pipe. These processes can just read from the inputs, and they can push onto their outputs without blocking. But if they try to read from an input, they do block until an input is available. And the interesting thing is that the communication pattern can actually be dependent on the data. So for example, I could pop an index off of one channel, and then use that index to determine which other channel I'll read from on the next time step. But at the same time, it is deterministic. So for a given series of input values on the streams, I'll always have the same communication pattern that I'm trying from the other inputs. So it's a deterministic model. That's a nice property. Let's see. What else to say here? There's actually a few recent ventures that are using con-process networks. So there's of commercial interest. For example, Ambrick is a startup that I think will be based on a con-process network for the programming model. Looking at another model called synchronous data flow, this is actually what we use in the StreamIt system. And compared to con-process networks, it's kind of a subset. It's a little bit more restrictive. So if you look at the space of all possible program behaviors, con-process networks are a pretty big piece of the space. And then synchronous data flow is kind of a subset of that space where you know more about the communication pattern at compile time. So for example, in synchronous data flow, the programmer actually declares how many items it will consume from each of its input channels on a given execution step. So there's no more data dependence regarding the communication pattern. It'll always input some items from some of the channels and produce some number of items to other channels. And this is a really nice property because it lets the compiler do the scheduling for you. So the compiler can see who's communicating to who in exactly what pattern. And then it can statically interleave the filters to guarantee that everyone has enough data to complete their computation. So there's a lot of interesting optimizations you can do here. That's why it's very attractive for StreamIt. And you can statically guarantee freedom from deadlock, which is a nice property to have. The last one I want to touch on is communicating sequential processes, or CSP. And in the space of program behaviors, it's kind of an overlapping set from con-process networks and adds a few new semantic behaviors. So the buffering model is basically rendezvous communication now. So there's no buffering in the system. Basically, anytime you send a value to another process, you have to block and wait until that process will actually receive that value from you. So everyone is rendezvousing at every communication step. So in addition to that, they have some sophisticated synchronization primitives. So you can, for example, discuss alternative behaviors that you have. You can do either one thing or another, which will introduce some non-determinism in the model, which could be a good or a bad thing, depending on the program you're trying to express. And pretty much the most well-known encapsulation of CSP is this Occam programming language, invented quite a while ago, and some people are still using that today. Any questions on the model of computations? OK. So now let me get into what StreamIt is. So StreamIt is basically a great language. It's a high-level, architecture-independent language. Oh, question in the back?
So with the CSP model,
yeah.
I'm trying to understand exactly what that means or how it's different. Is it just basically, what it's saying is you have a bunch of processes and they can send messages to each other?
So all of these models have that property.
They all fit into that. But it seemed like from your explanation of CSP,
right.
that was just sort of the essence of CSP.
Right. So CSP is usually associated with rendezvous communication. That's the set of programs that fit inside con-process networks. It's any communicating model where you basically have no buffering between the processes. Now, the piece that sits outside is usually lumped with CSP, or especially with Occam. They have a set of primitives that are richer in terms of synchronization. So for example, you can have guards on your communication. Don't execute this consumption from this channel until I see a certain value. So there's some more rich semantics there. And so that's the things that are usually outside the other models. Does that make sense? Other questions? OK. So StreamIt. OK, so StreamIt is architecture independent. It's basically a really nice syntactic model for interfacing with these lower level models of computation for streaming. And really, we have two goals in the StreamIt project. And the first is from the programmer side. So we want to improve the programmer's life when you're writing a parallel program. We want to make it easier for you to write a parallel program than you would have to do in C or a language like Java or any other language that you know. And at the same time, we want scalable and portable performance across the multi-cores. So an interesting thing these days, as you'll find, is it's often very hard to tempt a programmer to switch to your favorite language based solely on performance. Or at least this has been the story in the past. It may change looking forward, because it's a lot harder to get performance these days. But usually you have to offer them some other carrot to get them on board. And the carrot here is that it's really nice to program in. It's fun to program in. It's beautiful. It's a lot easier to program in StreamIt than it would be in something like C or Java for a certain class of programs. So that's how we get them on board. And then we also provide the performance. We're mostly based on the synchronous data flow model, in that when there are static communication patterns, we leverage that from the compiler side. Though I'll also tell you about some dynamic extensions that we have that's a much richer model of communication. So what have we been doing in the StreamIt project? We have kind of a dual thrust within our group building on this language. So the first thrust is from the programmability side, looking at applications and programmability. What can we fit into the streaming model? And we're also really pushing the optimizations. So what can you do from both a domain-specific optimization standpoint, that's kind of emulating a DSP engineer or a signal processing expert in the design flow, and also architecture-specific optimizations. So we've been compiling for a lot of parallel machines. And we were hoping we could have a full system for you guys, this IAP, so you could write it in StreamIt and hit the button, and it would work the whole way down to cell. Unfortunately, we're not quite there yet. But we do have a pretty robust compiler infrastructure. And you can download this off the web and play with it if you want to. One of our backends that we've released so far actually does go to a cluster of workstations. So it's kind of an MPI-like version of C. It uses pthreads for the parallelism model. And I mean, depending on what kind of a hacker you are, you actually might be able to lower that down onto cell. So some of this stuff you might be able to use if you have some initiative in there. And of course, we'd be willing to work with you on this as well. So we have a lot of optimizations in the tool flow. And actually, Saman will spend another lecture focusing on the StreamIt compiler and how we get performance out of this model. OK, so let's just jump right in and do the analog of hello world in StreamIt. I'm going to kind of walk you through the language and show you the interesting pieces from an intellectual standpoint, what's interesting about a streaming model that you can take away. So instead of hello world, we have a counter, since we're dealing with stream programs here. You're not usually doing text processing. So how do you write a counter? Well, there are two pieces to the program. The first is kind of the interconnect between the different components. That's what we have up here. We're saying the program is a pipeline with two stages. It has a source and it has a printer. And then we can write the source and the printer as filters. We call those basic building blocks filters in StreamIt. So the source will just have a variable x that it initializes to 0. And then we have a work function, which is automatically called by our runtime system every time through the steady state. So this work function will push one item onto the output channel, and it'll increment the value afterwards. Whereas the int printer at the bottom here will input one value, and its work function here just pops that value off the input tape and prints it to the output. Now, how do we run this thing? Well, there's no main function here, like you see in Hello World. Was there a comment? Oh, sorry.
Okay, never mind. The two meanings of push and two meanings of pop. One is actually doing the push, other one is declaring.
Yes, yeah. So the first push here is just declaring that this work function will push one item to the output tape. So this is the synchronous data flow aspect. We're associating an output rate with this work function. So it's a declaration here. Whereas this push is just actually executing the push onto the output. So how do we run this thing? Well, we compile it with the StreamIt compiler, strc into a binary. And then when we run for a given number of iterations. So you don't just call it once. Our model is that this is a continuous stream of data going through the program. And so when you run it for some number of iterations, or basically input or output items is what you're running it for. So if you run this for 4 iterations, it would print the values 0 through 3. So we can leverage this steady flow of data. Yeah, Amir?
It looks like it would print 1, 2, 3, 4 if you did that. You're pushing x plus plus.
I think the plus plus is executed after the push.
Push x plus plus.
So it starts at 0. So I think a postfix expression executes after the actual expression. Yeah. Yeah. Other questions? OK, so let's step up a level and look at what we have in StreamIt. So the first question is, how do you represent this connectivity between different building blocks? How do you represent streams? And if you look at traditional programming models, kind of the conventional wisdom is that a stream program is a graph. You have different nodes that are communicating to each other. And graphs are actually kind of hard to analyze. They're hard to represent. They're a little bit confusing. So the approach we decided to take in StreamIt is one of a structured computation graph. So instead of having arbitrary interconnections between the stages, we have a hierarchical description in which every individual stage has a single input and a single output. And then you can compose these together into higher level stages. Of course, there are some stages that do split and join with multiple inputs. We'll get to that. So the analog here is kind of analogous to structured control flow in your favorite imperative programming language. Of course, there was a day when everyone used go-to statements instead of having structured control flow. We got a fan of go-to statements in the audience? Okay, I'll get to you later. So, but the problem was, it's really hard to understand a program that's jumping all over the place, because there's no local reasoning you can have. You're jumping to this location, you're coming back a different way. It's hard to reason about program components. So when people went to structured control flow, they're just if-else, for loop statements, and those are the two basic constructs. You can basically express all kinds of computation in those simple primitives, and things got a lot simpler. And people objected at one point even, what about a finite state machine? Don't you need go-to statements for a finite state machine going from one state to another? And now everyone writes an FSM with a really simple idiom. You usually have a while loop around a case statement, right? You have a dispatch loop. So and now whenever you see that pattern, you can recognize, oh, there's a finite state machine. It's not just a set of go-tos. It's a finite state machine. So we think there are similar idioms in the streaming domain, and that's kind of the direction we're pushing from a design standpoint. So what are our structures that we have? Well, here are our structured streams. At the base, we have a filter. That's just the programmable unit, like I showed you. We have a pipeline, which just connects one stream to another in a sequence. So this gives you pipeline parallelism. There's a split join, where you have explicit parallelism in the stream. So I'll talk about what these splitters and joiners can do. It's basically a predefined pattern of scattering data to some child streams, and then gathering that data back into a single stream. So the whole construct still remains single input and single output. Likewise, the feedback loop is just a simple way to put a loop in your stream. And of course, these are hierarchical. So all of these green boxes can be any of the three constructs. So that's how you can have these hierarchical graphs. And again, since everything is single input, single output, you can really mix and match. Choose your favorite components, and they'll always fit together. You don't need to stitch multiple connections. So let's dive inside one of these filters now. And I gave you a feel for how they looked before, but here's a little more detail. So how do we program a filter? Well, a filter just transforms one stream into another stream. And here's transforming a stream of floating point numbers into another floating point number stream. It can take some parameters at the top. These are actually fixed at compile time in our model, which allows the compiler to really specialize the filter's code depending on the context in which it's being used. So for example, here we're inputting n and a frequency. And then we have two stages of execution. At initialization time, this runs once at the beginning of the whole program. We can calculate some weights, for example, from the frequency. And we can store those weights as a local variable. So you can think of this kind of like a Java class. You can have some member variables. You can retain state from one execution to the next. The work function is the closest thing to the main function. This is called repeatedly in the steady state. And here are the I/O rates of the work function. This filter actually peaks at some data items. That means that it inspects more items on the input channel than it actually consumes on every iteration. So we'll look at n input items, and we'll push one new item onto the output, and pop one item from the input tape every time we execute. So here we have a sliding window computation. It means the next time through, we'll just slide this window up by one and inspect the next n items on the input tape. And inside the work function, you can have pretty much general purpose code. Right now, we disallow pointers and a few other things to keep things simple. But the idea is this is general purpose imperative code inside the work function. Now, what's nice about this representation of a filter is, well, for one thing, is this peak function. So what we really have is a nice representation of the data pattern that you're reading the data on the input channel. And if you look at this, for example, in a language like C, it's a lot messier. So usually when you're doing buffer management, you have to do some modulo operations. You have to keep a circular buffer of your live data and increase a head or a tail pointer and mod around the side with some kind of modulo operation. And for a compiler, this is a real nightmare, because modulo operations are kind of the worst thing to analyze. You can't see what it's actually trying to read. And if you want to map this buffer to a network or to a combined communication with some other actor or filter in the graph, it's pretty much impossible. So here we're exposing that all to the compiler, and you'll see how that can make a difference. And also, it's just a lot easier to program. I mean, I don't like looking at this code, so I'm going to go to the next slide. OK, so how do we piece things together? So let's just build some higher level components. So here's a pipeline of 2 components. And we already saw a pipeline. You can just add one component after another. And add just basically has the effect of making a queue and just queuing up all of the components that you added and connecting them one after another. So here we have a bandpass filter. By connecting a low-pass filter and feeding its output into a high-pass filter, end up with a bandpass filter. OK, what about a split join? How do we make those? So a split join has an add statement as well. And here we're adding components in a loop. So what this means is now when we say add, we're actually adding from left to right. So instead of going top to down, we're adding from left to right across the split join. And we can actually do that in a loop. So here we're inputting a parameter n. And depending on that value, we'll add n bandpass filters to this split join. So this is kind of cool, right? Because you can input a parameter, and that parameter actually affects the structure of your graph. So this graph is unrolled at compile time by our compiler, constructing a big sequence of computations. And we can resolve the structure and communication pattern in that graph, and then map it to the underlying substrate when we compile. Also to notice here are the splitter and the joiner. So we have a predefined set of splitters and joiners. I'll go into more detail later. But here we're just duplicating the data to every one of these parallel components and then doing a round-robin join pattern where we bring them back together into a single output stream. And if you want to do an equalizer, you basically need an adder at the bottom to add the different components together. And another thing you can notice here is that we have some inlining going on. So we actually embedded this split join inside a higher level pipeline. So what this does is it prevents you from having to name every component of your stream. You can have a single stream definition with lots of nested components. And the natural extension is you can basically scale up to basically the natural size of a procedure, just like you would in an imperative language. And here's, for example, an FM radio, where we have a few inline components. And the interesting thing here is that there's a pretty good correspondence between the lines of the text and the actual structure of the graph. And that's something that's hard to find in an imperative language. I mean, if you want to, for example, stitch nodes together with edges, it's often very hard to visualize the resulting structure of the graph that you have. But here, if you just go through the program, you can see that the A to D component goes right over to the A to D, the demodulator to the demodulator, and so on. And even for the parallel components, you can kind of piece them together. So that's kind of how we think of building programs. Any questions so far? OK, so this is kind of how you'd go about programming in StreamIt. But programming is kind of a chug-and-plug activity, right? Nobody wants to be a code monkey. The reason we're all here is to see what's beautiful about this programming model. Right? Don Knuth said this, famous computer scientist from Stanford during his Turing Award lecture. Some programs are elegant, some are exquisite, they are absolutely sparkling. My claim is that it's possible to write grand programs, noble programs, truly magnificent ones. Right? We want the best programs possible. It's not just about making it work. We want really beautiful programs. So what's beautiful about the streaming domain? What can you go away with and say, wow, that was a really beautiful expression of the computation? Well, for me, I think one of the interesting things here is the split join construct. Split joins can really be beautiful. Some mornings I just wake up and I'm like, I'm so glad I live in a world with split joins, And now split joins will be part of your world. You can say this tomorrow. This is just wonderful. So OK, what do we have in the split join constructs? You can duplicate data. You can do a round-robin communication pattern from one to another, or a round-robin join. Now, the duplicate is pretty simple. You just take the input stream and duplicate it to all the children. No problem. What do you do for a round-robin? Well, you pass n items from the input to a given child. So for example, if n is 1, we'll just distribute 1 at a time to the child streams. And you get a pattern like this, a round-robin just going across. And you can do the same thing on the joiner side. Let's say you're joining with a factor of 1. You're just reading from the children and putting them into a single stream. OK, so this is pretty colorful, but nothing too fancy yet. Let's consider a different round-robin factor. So a round-robin of 2 means that we peel off 2 items from the input and pass those items to the first output. OK, there actually is going to be a quiz on this. Ask questions if this doesn't make sense. OK, pass the next 2 items, and 2 items round-robin like that. And you can actually have non-uniform weights if you want to. So on the right, let's say we're doing round robin 1, 2, 3. That means we pass 1 item from the first stream, 2 items from the next stream, and then 3 items from the third stream. OK, pretty simple. We're just doing 1, 2, and 3, and so on. Does this make sense? I'm going to build on this. So any questions? OK, so this was colorful, but this isn't totally beautiful yet. So what's beautiful about this? Well, let's see how you might write a matrix transpose. OK, something you guys have probably all written at one point in your life is transposing a matrix. Let's say this matrix has m rows, and it has n columns going across. And we're starting with a representation in which the stream is basically, I think this is row major order. The first thing that you're doing is going across the rows before you're going to the next row. Sorry, you're going across the columns and then down to the next row. So it's zigzagging like this. And you want to pass through a transpose, so you zigzag the other way. You do the first column up and then the next column, and so on. And this comes up a lot in a stream program. So it turns out you can represent this as a split join. Oh, that's not good. Just in my moment of glory as well. OK, yeah, slides. You can download slides. Actually, I can do this on the board. This is the thinking part anyway. Yeah, could you just bring up Gmail? I have a backup on Gmail. Can we focus on the board? So this is going to be a little exercise anyway. OK. Here's what we had. We had m rows, n columns. We started with an interleaving like this. Right, and we want to go into a split join. And this will be a round robin construct. And what I want you to do is fill in the round robin weight and also the number of streams. And you can have a round robin at the bottom. And when it comes out, you want the opposite interleaving. This is m and n. OK, so there are three unknowns here. What you're doing the round robin by. Can you guys see that over there? How many parallel streams there are, and what you're joining the round robin by. OK, so I'm going to give you a minute to think about this. Try to think about this. See if you can figure out what these constants are. You just basically want to read from this data in a row major pattern, m rows and n columns, and end up with something that's column major. What are the values for the constants? Does that make sense? Ask a question if it doesn't make sense. Yeah?
So we assume that the values are based on the line that you drew. Going across. That's like a straight line.
Straight.
Right. Those values are coming down this stream. You have a one-dimensional stream. It's interleaved like this, so you'll be reading them like this.
Okay.
And then you output a one-dimensional stream that is threading the columns. Does that make sense? Somebody ask another question. Yeah.
So, in actual matrix transpose codes, as I understand it, nobody actually does it sequentially like that because of locality issues. Instead, it's broken up into blocks.
So there are ways to optimize this.
And can you after you've sort of serialized it, can you then capture the
Actually, what happens is you
Yeah.
can think each of the node as a block itself. So you can hierarchically do that. So normally what happens is you move the blocks, and inside the blocks you have to do it again. So you can do it at 2 levels, basically.
Just say, oh, we went from n by m to n by m, and it's now by row instead of by column.
Any hypotheses? Someone?
Is it n for the first one and m for the second?
Where's my shot? Oh. OK. What do we have?
N for the first one and m for the second.
M, and
Same for the put it back in, it's m.
M?
Yes.
OK, undecided.
Wait.
OK, this is a hypothesis. Other hypotheses?
NM1.
NM1. OK, anyone else? Any amendments?
111.
111?
Yeah.
Okay, lottery is closing. Yep.
1 nm.
1 nm. 1 nm. Okay. Any last call? Okay, I believe 2 of the ones submitted are correct. Wait, is this and yeah. Okay, I think this nm1 works and 1 nm works. So let me explain the 1 nm. This is how I like to think about it. One way to think about this is we just want to move the whole matrix. You doing okay, Simon? Yeah. We just want to move the whole matrix into the split join. So the way we can do that is have n columns of the split join, since we have n columns of the matrix. And what we'll do is we'll just do a round robin one at a time from the columns of the matrix into the columns of the split join. So we'll take the first element, send it to the left, next element, next column, and so on. So we get the whole matrix here. Now we want to read it out column-wise, so we'll do a joiner of m. We'll read m from the left stream. That'll read all m items in the column, send it out, and then m items in the next column, and send it out. Does that make sense? How many people understood that? All right. So if you think about it, you can also do it in nm1. That's basically, yeah, it's very similar. Okay, there we were. And yes, we can do 1 nm. We'll basically read the matrix down and then pull it down into columns. And it's very easy to write this as a transpose. So we just have a transpose filter in which we're doing nothing, no computation in the actual rows or actual contents of the split join. And we just split the data by 1, have n different identity filters, and then join it back together by m. Any questions about this? Kind of an interesting way to write a transpose. OK, so there's one more opportunity to shine here. And that's a little more interesting permutation called a bit reversed ordering. So this comes up in an FFT and in other algorithms. The permutation here is that we're taking the data at the index n. And let's say n has binary digits b0, b1, up through bk. And we want to rearrange that data so this data goes to a different index with the reversed bits of its index. So if it was at index n before, it ends up at bk down to b1, b0. So for example, let's just look at 3-digit binary numbers. If we have 0, 0, 0, this is one input item. We're reversing those digits. You still get 0, 0, 0. Item at index 1 will be 0, 0, 1. We want to reorder that to index 4. OK, 1, 0, 0. 0, 1, 0 stays the same. 0, 1, 1 goes to 1, 1, 0, shifts over. And from there on, it's symmetric. Sorry? Oh, OK. So here I'm writing the indices. So I'm not writing the data. This is index 0, 1, 2, 3 up through index 8, or index 7. OK, and on the bottom, you have indices 0 through 7. So the data will actually be moved, reordered like this. Does that make sense? It's a reordering of data. Transformation makes sense? Other questions? OK, so it turns out you can write this as a split join. And you just need 3 different weights for the round robins. OK, round robin with 1 weight on the top here, and 2 different round robin weights on the bottom. And here I'm assuming you have 3 binary digits in your index. So you're reordering in groups of 8. OK, so let me give you a second to think about this. What are the values for these weights? I'll give you a hint in just a second. Or ask another question.
That's another question.
Yep.
Maybe that's related to the values of the weights, but why would we want to write an FFT this way? Is there like
So what we're doing here is we're exposing the communication pattern. That's the thing. If you write this in an imperative way, you end up basically having, you're conflating basically the data dependencies with the reordering pattern. So what I'm trying to convey here is how you can use the streaming model to show how you're sending data around. Because when you're on an architecture like Cell, everything is about the data motion. You're taking data from one place and you're trying to efficiently get it to the producers or the consumers. And you really need to, the compiler needs to understand the data motion. And also, it's just another way of writing it, which I think is actually easier to understand once you see it. It's a way to think about the actual reordering from a theoretical standpoint. Any wagers on this? So what we want to do, if you think about the bit reverse ordering, what we want to do is distribute the data by the low order bits, and then gather the data by the high order bits. So you want a fine-grained parity when you're shuffling. You could also do it the other way around. It's totally symmetrical. But one way to think about it is you want a fine-grained parity when you're distributing data, and then coarse-grained when you're coming together. Anyone see it? I'll give you 10 more seconds. Saman?
It's a hard one.
Yeah, it is a little bit tricky. OK, well, let me explain how it works. So 1, 2, and 4. OK, so what these round-robin 1 splitters do is these are basically the fine-grained parity. So OK, this first round-robin, that'll send all the even bits to the left and all the odd values to the right. Right, that's the lowest order bit, because it's doing every other one, shuffling it left and right. So this round-robin is seeing only the even values. Now it's going to split them up based on who's divisible by 4. Now we'll go to the left or go to the right. This is basically shuffling in the order of the bits from low order bits to high order bits. So these will be ordered by in terms of their low order bits. And now we just want to read them out from left to right. Just take the order that we made with those round robins and read them out from left to right. And since we have 8 values, you can do that just by chunking them up. We'll read 2, 2, and then we'll read these 2, 2 and 2, and output all 8. Does that make sense? OK, so yeah, it's a little bit clever, because I think it's a nice way of thinking about what a bit reverse ordering means. And you can write this in a very general way. You just have a recursive bit reverse filter for n values. In the base case, you only have 2, so there's no reordering to do when you think about it. So you're not doing any computation. Otherwise, you have a round robin, split in half, and then have a coarse-grained joiner. So you get a structure like this if you're as you're building up, just distributing and then bringing back together in a coarse-grained way. OK. Let's see. How do I want to do this? OK, so one thing to notice, just one more example of a split join question.
What's identity complex?
OK, good. So in general, at the base of this hierarchy, we could have added some other filter to do some computation. Identity just means we're doing no computation. It's a predefined filter that just does nothing.
And complex data.
On complex data. Sorry, this is a templated filter. So we're reordering complex values, and we're passing the input to the output. Amir?
This supports templated pipelines, filters?
In general, the language does not have support for templates. We only do it for these base classes. That's more of an implementation detail.
Okay, so there's
Yeah.
polymorphism.
Right now there isn't, but nothing fundamental there. Yeah. Other questions? Yeah.
I just know that there are 2 filters after that. But,
2 filters. Wait, sorry. Here?
like their very first split at the top.
OK. So we have 2 add statements between the split and the join. So that branches to 2 parallel streams. Is that your question?
Yeah. Then how do you know that there's not like 3?
So the compiler will analyze this at compile time, and it'll know these values of n and propagate them down at compile time. So it'll basically symbolically evaluate this code, see there are 2 branches, and you can unroll this communication pattern.
I think another way of thinking about it is each add statement conceptually adds another branch in your split join.
Okay.
So you have 2
You can
branch
put a
statements.
box round. Right? This is a box.
Yeah, sure.
And there's another box.
So this is about to get clearer, actually. Other questions?
So it's basically counting sort of radix 2.
That's one way to think about it, yeah. Counting, wait, say again? Counting sort?
Radix sort?
Radix sort, right. OK, well, is it sorting though? It's not really sorting.
Well, it's not really sort.
It's a permutation. You could do a radix sort this way. So actually, what I want to show next is how you can morph this program into a merge sort by changing only a few lines. So OK, look carefully, don't blink. OK, there's merge sort. So very similar pattern. This is one of those idioms. It's a recursive idiom with split joins. But now in the base case, we have a sort. So we basically branch down. What we ended up with was a sort in the base case. We're just sorting a few values. and we call merge sort twice again, and then we do a merge. So instead of identity at the base case here, we now have a basic sorting routine, and then we merge those results from both sides. And the only thing I changed in terms of the communication rates is to be more efficient, we just distributed data in chunks instead of doing a fine-grained splitting. Actually, you can do it however you want in a merge sort, but this is chunked up. And let's just zoom in here. This is how a merge sort looks in StreamIt. So we split the data 2 ways, both directions, come together, do a sort on both sides, and then you merge. And so by having this, you can interleave pipelines and split joins like this. So you have these hierarchical structures that are coming back together. Does this make sense? OK. So I'm going to hold off on messaging, actually. Let me see. What do I want to cover? OK, let me actually skip to the end. Oh, I can show you this. Yeah, I'm going to cut short a little bit. So here's how other programs look written in StreamIt. OK, you can have a bitonic sort. Yeah, so you see a lot of these regular structures, and the compiler can unroll this and then map this to the substrate. This is how an FFT looks. It's quite an elegant implementation of an FFT. It'd be good to go into in more detail. You can do things like block matrix multiply. You don't always have to have column or row-wise ordering. It's natural to split things up like this. We have a lot of DSP algorithms, a filter bank, FM radio with equalizer, radar array front end. Here's an MP3 decoder. And let's see, I'm going to skip this section and just give you a taste for the end here. Skipping 100 slides. Yeah. OK, so I just want to give you a feel. Our biggest program written in StreamIt so far is the complete MPEG-2 encoder and decoder. So here's the MPEG-2 decoder, and I think you've seen block diagrams of this already in the class. And so it's a pretty natural expression. You can really get a feel for the high-level structure of the algorithm mapping down. And for example, here in the top, we're doing the spatial decoding, looking inside each frame. Whereas at the bottom, we're doing the temporal decoding between 2 frames, the motion compensation. And one thing that I didn't have a chance to mention is that we have a concept of teleport messaging. What this means is I showed you how the steady state flow of data goes between these actors in the stream. But sometimes you want to control the stream as well. For example, this is the variable length decoder at the top. It's parsing the input data. It might want to change how the processing is happening downstream. For example, say that you have, in this case, you have different picture types coming in, and you want to tell other components to change their processing based on a non-local effect. Now, that's hard to do if you just want static data rates. But what we have is this notion of limited dynamism, where you're basically poking into somebody else's stream. And we let you do that very precisely. I didn't have time to go into the details, but you can basically synchronize the arrival of these messages with the data that's also flowing through the stream. And so in this case, we're sending through the picture type, and it really simplifies the program code. Didn't have time for details, but why don't we put it in the slides anyway, if you're interested. And if you do a similar communication pattern in C, it's a little bit of a nightmare. You have all these different basically memory spaces, different files, and the control information is basically going left and right all over. So this really helps both the compiler and the programmer as well in StreamIt. So this is all implemented. It's about 2,000 lines of code in StreamIt, which is about 2/3 of the size of the C code, taking into account similar functionality there. And it's a pretty big program. You can write 48 static streams, and then we expand that to more than 600 instantiated filters. So this gives you a lot of flexibility when you're trying to get some parallelism. Question?
When you compile it down, how big is the bytes compared to C?
Oh, the object code, you mean? OK, so right now, our current implementation, we duplicate a lot of code. Okay. So it ends up being bigger than it needs to be. There's no reason for us to do that. That's kind of we have a research compiler that makes that easy.
OK, so object-wise, it's not bigger. It's smaller. It's bigger than C?
Object-wise, we still need to do that comparison. Okay. Yeah, that's a good question. Yeah. Other questions? OK, so let me cut to the end. OK, so we have the StreamIt language, and we think it really preserves the program structure. It's a new way of thinking about how you orchestrate the data reordering with the split joins, showing you who's communicating to who, and how you can stitch together different pieces in your program development. And again, really our goal is to get this scalable multi-core performance. But you can't get people on board just on a performance bet. You need to show them a new programming model that actually makes their lives easier. So that's what we're working on. And thanks for listening. Any last question? Yeah.
So like in the MPEG decoder, you had a lot of computations that produced values that were not sequential streams. Like for example, the output of a a discrete cosine transform is not a stream of pixels. You're going to have coefficients and such like that, which are in logical sort of chunks.
Yeah. So you don't. Yes. Sure. So depending on the granularity of the computation, you don't need to pass individual values over the stream. For example, you can have a stream that inputs a whole array at a time. And so we basically advocate that if you have something that coarse-grained, you should be passing an array or a macro block in the case of MPEG, or a set of coefficients in a structure. So when you have coarse-grained parallelism, you write your program in a coarse-grained way. The fine-grained things I showed for the bit interleaving and so on is more for the fine-grained programs.
Can you do both? In the sense that, like, can you stream over an array?
Right.
A stream of streams, so to speak?
Right. So there's an interesting multi-dimensional problem there. Right now, we've taken a one-dimensional approach. So far, basically, the programmer has to set an iteration order and end up with a one-dimensional stream coming into and out of every filter. We're working on extending that. Yeah, when you have basically streams of two-dimensional data, you'd like the freedom to either iterate basically in time or in space, depending on what you're doing. And so I think that's more of a research problem. So far, we've just been doing a one-dimensional representation. Yeah, that's a good point. Other question? Yeah.
Why did you decide on the synchronous data flow model as opposed to something more general?
Yep. So our philosophy has been that you want to start with the most kind of basic block of a stream program and optimize it really well. And then you can stitch those together into higher level blocks. So we think of synchronous data flow as being kind of the basic block of streaming. You know what's coming in, you know what's coming out. And even if you have a more general model, there'll be pieces that fit under their synchronous data flow model. And so we saw a lot of optimization opportunities in there. And really knowing those I/O rates can let you do a lot of things that you can't do in a general model. So we wanted to get the simple case right first. And actually, kind of our focus now is on expanding. And how do you look at the heterogeneous systems? And how do you optimize more dynamic systems? Yeah. Other question? OK.
So there is
yes. You can check out our webpage. Yeah, if you Google for StreamIt, I'm sure you can find it. Yeah, we have a public release. Yeah, send us any problems. We want to actually, it's a good test. We want to make sure it works for everyone. So, but I mean, we've had hundreds of downloads. There are a lot of people using StreamIt, so it shouldn't break if you download it. Yeah. Okay, good. Thanks.